Hey Tim, ik wil even een video maken over wat pointers zijn. Misschien al dan niet voor mezelf, maar ook voor jou. Want ik hoorde dat je C leerde en ja, ik dacht, awesome. Dus ik denk dat er namelijk een paar dingen met pointers zijn die vaak niet worden uitgelegd aan studenten. En als je die dingen extra uitlegt, then it all makes so much more sense. So, and the reason for that is, let's switch to English. The reason for that is there are basically two parts of the explanation. The first part is what pointers actually are, and the second part is what reality is. So, what they are and reality. Because it's kind of different, right? So, reality. Yeah, awesome. So let's start with what pointers are. So, basically, you have memory, right? Let's just say, our memory is like this, right? Boop, boop, boop. Our computer doesn't have a lot of memory, and well, in that memory, you have values stored. Let's say, so computer addresses are normally denoted in hex. So let's do that here as well. So this is null x null. This is null x 1000. Let's say 1000. Or no, let's actually do it by 4 bytes. So that would mean this is I forgot what 4 bytes are. Yeah, let's do 1000 then. Okay, and this is right. Okay, got the memory up. So let's say that a value, so somewhere in that memory lives a value here, right? So 4 byte, let's say it's a 4 byte value. It's a 5 of type let's annotate here, unsigned integer T32. I think you write it like that. So an unsigned integer just means so this part means that it's positive, and then signed integer is negative or positive, basically. Okay. And this means this part means that it is 32-bit in C. Okay, so you have pointers. So let's say we have a pointer. Pointers are, I think, 4 bytes as well. Not sure. I think in a lot of cases are 4 bytes. So let's say you have a pointer here. So let's call it num pointer. So yeah, so num pointer, and it points to this thing, and this thing is at I don't know, address. Let's call this, it's high up. So let's call this address. Let's call this at address this, right? So then in code, if you have a pointer, basically you have a block that basically the same 4 byte block that denotes the address. Now there are a couple of interesting things here. And this pointer has a variable name. So let's say we call this x, right? So this is a variable x. So let's say, so let's say ux x equals 5. That's basically what this part is, right? Then say, for example, then this is a this is a u int t32. Let's say num pointer. Doesn't really matter. Num pointer. And basically, currently, this value means that it's equal to the address of x, and the address of operator is this thing, and x is this. And the address of x is this thing, so this value then, the address of x is this thing, right? So then the value gets transplanted in there. So that's nice. That's how it works. This is what a pointer is. So basically then, you can already imagine, when you then do, for example, printf, right? Or for the hipsters, fprintf in stdr, because it doesn't buffer, it immediately prints instead of on standard out. When you then print, let's say you print this in a hex, right? In a hex format. So you can also do the normal number format, but this would be the hex format, right? Then obviously what you would get, this would just display, this would print this, right? And if you would have a D, then it would print the numerical version of that. Okay, so now the cool thing is in C you have two operators for pointers, two pointer operators. Already a denoted one. I'm gonna do the other one, operators, right? So you have the star, which means to dereference, which is a very fancy way of saying that you're unpacking the value at the reference it holds. So currently the reference that it holds, right, is this address, because that's literally what's in there, right? So then basically the D reference of that is kind of like the unpacking of it, which is the value at that place, which is 5. So basically what a star operator does is it's kind of like it goes here, take the value, and boom, now we have it. That's more or less what it does. Then the second you can also call this, if you would want, if you think this is easier, the instead of the dereference, which is the formal name, just call it, because this is just an as valid name in my opinion, the value at operator. Now this thing I always call the address of operator. And basically what this does is, well, it checks the address of something. So let me ask you a question. So you can think about this yourself. Let's see if I have space here. Yeah. So first question is, what's the address of X? Or maybe I should, address of. Maybe we should do it this way. What's the address of X? Right? Well, you'd be like, simple, the address of X is whatever is here, because that's where X lives. Let me ask you another question. What's the address of a num pointer? You can pause the video to think about it. Well, the first question is in this memory layout, right? Where does num pointer live? And you'd be like, well, it lives here, of course. Like, it's there. And then you would also point out you didn't specify a fictional address for it. So let me just do that now. Let's say it's 0x100, right? And then you'd be like, okay, well then it's easy. Then the answer to your questions are this and this. and you'll be right. And the interesting thing is then that a pointer is just a memory address as a value. Here, it's this value, right? But because of the two operators, you can specify two other values. Namely, this would be the one with the address of operator, and that one would be with the star operator, right? And then this one itself, this one itself would be if you just used do nothing, or like use the variable name. So I think that's quite interesting, because that's really the magic of pointers. So in that sense, I think if you really want to play around with it, what you should do, right, is by the way, always import standard IO, of course, if you're gonna do this. But like, you could print sure, why not? Yeah, I print everything in X nowadays. I mean, if it's not really important how or what. So when you think about it, you can print them all. So you can print, heck, no, you could go even further with this. Let me actually draw the whole. Let me draw them all. So the first one is going to be address of. Second one is going to be the dereference of. Then we're going to have an address of here, and here we go. So the address of num pointer, right? Then you have comma. Oof, this dereference is too close, because I always like to do it like this. Then the num pointer itself. It's a good question for you. What do you think all these things are? And then, verify it. And then you have the dereference, or the value at num pointer, which is the value at its address, right? Then you have the address of X, and you have X. No, but you could also do you could also do star X. You could, but I think the C compiler would give you hell, because it's not a pointer. Because only a pointer is allowed to dereference. There are probably exceptions to this, but like I think in conventional C code that's the case. Though with this you can also do this for normal variables, and I think it's actually quite a nice thing. So, well, what do you think the answers are to all these questions? You can pause the video and you can think about it for yourself. I'm just gonna write them down here. So, what's the address of num pointer? Well, the address of num pointer is this, right? 0x0100. Then the question is, what's the value of num pointer? Well, the value of num pointer is I suppose value at address is a better one instead of dereference. So the question is, what's the value at the address of num pointer? Because that's really what this thing implies, right? So, well, that answer is 5. Then what's the address at X? Well, that is this one again. And what's the value at it? 5. So that's like how pointers. So in this is all what they are. This is all 1, right? So this is all this is all this. So let me box it in a bit better, right? Cool. So this whole thing is 1. I think this is quite clear what it is, right? By the way, if you want to know about the etymology of this, I even asked a Stack Overflow question on it, so you can check that out. Basically, the D part is like that you unpack it, the D part. Oh. Okay, so let's go a bit further. Let's go to reality. The part that I always wanted people to explain to me, but they wouldn't. And reality. So in reality is there are a couple of extra concepts that you need to know, because the thing is, conceptually, what we talked about, it's all true. This is so one is really how pointers work, right? This is how pointers work. But the thing is, reality has management. Reality has management. You know what managers do? They always screw it up. That's what managers do. And for reasons, right? Like not just because they can. No. That would be too easy. Like no management initially, hopefully, is justified by just screwing things over. No. It's because there's a need to, and that's because in an operating system, right? In an operating system, you have the kernel, obviously, and you have user space. And in user space, you have multiple programs: program 1, program 2, program 3. Now, the thing to note here, these things, they need to happen in a peaceful way. So they need to happen peacefully. And that's why management exists. Because imagine you're a program. So in memory again. So with memory, right? Now you're just this whole program. Let's call you P1. Now let's say that the kernel is operating here, right? Now imagine you have a pointer. And with that pointer, you're dereferencing a value at somewhere in kernel land. Imagine if this would be allowed and you could read values from there, you could write values from there. Heck, you could just, read write from the kernel. You know what that implies? That implies that you hack the system. And managers, they don't like it. They don't like it that you hack the system. They're like, nope, let's not do that. So the kernel allows you basically tells you where you're allowed to use pointers. It tells you when you are not allowed to use pointers. Not allowed to use pointers. So the kernel tells you when you're not allowed to use pointers. That's the whole thing. And that's the reality. And to better understand that, to how this reality really works, I think you need to understand about the stack and the heap from the perspective of pointers. So the stack is like a memory data structure that acts like a stack. So it just goes upwards. Though in reality, in actual memory, so let's say this is actual memory, the stack, let's just call this the stack, actually grows downwards in reality. But it's still a stack. It just grows downwards. It's like a little blue little blue stalactite in like a cave, you know, they grow downwards in cave. Really cool. So, and then you have the heap. The heap is, just memory allocated by the program, and the heap starts from here and it grows upwards. Now you can see that there are issues there because they can clash and then you're out of memory. But another thing is, this is all fine and dandy, but somewhere you just have the whole kernel. And this here, this whole thing is actually user space. Okay, that's so cool. So what is important here? Well, the thing is, a stack works per function. Works per function. Every function sets up, every function set up their own stack frame. So let me show you what I mean by this. So in the stack frame, you have, so let's say you have 3 functions, right? You have f1, f2, and f3. Let's suppose you have a couple of variables statically allocated. So this one has, I don't know, int x and int y. This one has a string char equals 5 equals 7 equals hello. Woo, cool. And this one has an array of integers, so numbers. So int 8 numbers. I think you can statically allocate. Yeah, I think you could, which would, oh no wait, this is not how you write it. I think, so I'm not always super clear on the syntax. I think it's here. And if you want to statically allocate it, you do curly braces and then 1. Right. So now the thing is, that basically means that each of these have a stack. So this is a stack frame of function 3, this is a stack frame of function 2, and this is a stack frame of function 1. And now the stack doesn't build up arbitrarily. They build up on how they're called. So they build on, let's see, on a LIFO. I think it's LIFO, last in, first out. So in this particular case, right, say you have some code. So then it would be, I think, F3 would be called first. F2 would be called next. And no, sorry, I think that's not even true. I think this would be inside F3 because the moment when a function returns, that's also when the stack frame gets destroyed. So let's just make a simple comment. It's inside F3. And this should then be inside F2. Right? Okay. So, yeah. So it works per function. They have one stack frame, and the moment the moment a function returns, a stack frame gets destroyed. Okay, so another way to think about stack frames is all the local variables of a function go there. Now, since you start from the main function, right, and you return 0 or something, it basically means for your purposes, everything is in a function. And there's one exception, and that's the heap. When does the heap occur? Well, simple. So when you allocate memory with C explicitly, then you go to the heap. So explicit, I will point with all of this, by the way. Explicit memory allocation. Well, that means heap. So what's an example of that? Okay, let's say you want to have a character array, just to keep things simple. Also because I don't use it a lot. So letters, right? Car letters equals let's say malloc. And I think the way to really do this is to say size. Let me get color here. Size of, I think you write it like that, not totally sure. Size of car. And then running out of space. Size of car times well, the amount that you want, right? So let's say, I don't know, 27. That means 27 characters. So this gets allocated to the heap. By the way, one interesting implication of this is that when you have a pointer, that's one reality thing. When you have a pointer, so this is a pointer, pointing to somewhere on the stack frame, then you have an issue in some cases, because in some cases, well, no, let's say that you keep this pointer around, right? And at one point, this function returns. That means that this gets destroyed. Then where does this point to? Or in another case, the question then is, did the value in that pointer then change? And if it didn't, what would happen if you dereference that pointer? So if you take the value at the address it points to. Think about it. You can pause the video for a bit and think about it. The real answer, and so this is one reason why you need to know about stack frames, because I ran into this bug quite recently. So the answer is the answer is that the pointer still has the same value because the memory address didn't change, but this thing got deleted. So now this part belongs to the kernel, or someone else basically. It could also be a user-based program, someone else. It belongs to the kernel if no one else took it, and otherwise it's another program. So that means the value at that place can change. And in some cases, In some cases, C recognizes that you're screwing up and it's crashing your program, and in some cases it doesn't. Well, let me go back to crashing programs later on. So that's one real thing. But I was talking about the heap. The heap. Or in other words, this thing. So one different thing is, and I think that's why I jumped back, is in the heap, values don't get destroyed unless you deallocate or quit the program. Don't get destroyed. Destroyed unless you deallocate or quit. Exit the program. Or stop it, right? So, well, that's the thing, because it has so that really just exaggerates, exaggerates the fact, or however you call it, that this stuff, the stack is good for local. It's really good for local. And this is really good for data, the heap, or more global, like, I don't know, for multiple functions, right? Yeah, basically that. So that's a good point. That's the thing. And okay, so the point is though, and that you also have a similar issue in the heap, right? That's one telling about the heap. So that's like, so the counterpart of malloc for memory allocate, right, is free. So it's free memory. So you freeze memory. You free memory. And the thing is, when you free memory, but you keep the pointer around, then you again have a pointer that points to nothing, right? So let's imagine you have a heap. And in that heap, you allocated this part, right? Now let's say, I don't know, in the stack, it doesn't really matter. You have somewhere, you have a pointer, right? And it points, the value of the memory address points to here, right? So let's say this is 500, then it secretly has 500 in there, right? So let's say the value here is 15, I don't know, or just some array or something, right? The moment you say, free this place, then all this memory, right, gets deallocated. So now I got a question for you, Tim. If this pointer, right, if this pointer has a value, so the pointer here, if that pointer here has a value of 0x500 and points to here and has deallocated memory, what does it point to? Well, it points to a garbage value. So it points to a garbage value. And, well, that's bad. Because nothing bad will happen unless you take the value at that address. And yeah, you could get a garbage value back, or it could again crash. So currently, in part 2, in reality, I talked about 3 things. I talked about kernel versus user space. I talked about the fact the kernel is the manager, right? I talked about one pointer issue on the stack. And I talked about a similar similar issue on the heap. Okay, so let's now go to 2b. To B answers the question, when will my program crash for dereferencing nonsense or badly allocated memory? And I don't fully know the answer to this question, but I know it well enough. And the answer really is, did the kernel take it back? Did the kernel take it back? Right? That's one question. Another question is, does another program? Because if that's the answer, then you only have a garbage value, I think. Well, let's go back to that in a little bit. Does another program have it? Because if another program has it, because if another program has it, it will crash. Now, there's a modifying question to did the kernel take it back, which is, well, it's not necessarily a modifying question, but it's basically, is the memory, is the value of the pointer and remember, the value of a pointer itself is just an address. If you don't believe me, let's scroll back to the first example. Yeah, which is here. See, the value of a pointer is this thing. It's just an address. Now the value at the address of the pointer, called dereferencing, that's this thing. By the way, these things are also called, obviously, unary operations, right? Because they only need one operand. Okay, cool. Sorry about that. So, okay, cool. So let's go back. So, my point is, fine, okay. Now, so is the value of the pointer, and again, the value of a pointer is just an address. In kernel, an address in kernel space because this will mean crash, or in user space. Because if it's in user space, then really it points back to these two. Can I do it? Yeah. Okay. right? It points back to these questions. So that's when it crashes. How does it crashes? What does it say? So the error really always is segmentation fault. So the thing is, that's different, right? Like, because basically the reality of pointers is it can crash, and it can crash because of the kernel. And but like, if you wouldn't have a kernel, right? If you wouldn't have a kernel, then I would not have to explain this. I would only have to explain what they are, and they would always work the same. And the thing is, there is one little trick that you need to Google for, because I don't know of it by heart. But there's basically a trick in which you can, in which you can form the reality a lot more to what they are, and that is by having an interrupt handler. So you can have an interrupt handler. Now, for people who watch this, a handler is a fancy way, it's a fancy word for function. Fancy word for function. An interrupt is, in this case, the kernel interrupting your program. And when it does it with a segmentation fault, it's crashing it. No, not even. I think it's almost always a crash. But an interrupt handler, an interrupt handler can handle and therefore mitigate a crash. Now, that still doesn't mean that your pointer will dereference, because the kernel still may not allow it, but at least your program will not crash. And this is a thing that I learned about yesterday. So you can Google it. It's something like I think it's something called SIGSEC-V, interrupt handler. And then basically your pointer may still not be able to get the value at the address of some kernel space program or another program, but at least your program will not crash. Therefore, bringing reality a bit closer to what pointers actually are. And that was 2P. And basically, that is the whole story on pointers. What they are and reality. Yep. I don't have brown. Well, let's have a blackish tree. The story of pointers. And that's really the end of my story. story of pointers, what they are, and how they go about it in the real world. Thanks for listening, and well, I hope you learned something, and I hope it wasn't all old material.